This video is going to be about rotational curves in the mass of galaxies, and how that provides evidence for dark matter. You can think of a galaxy as having basically two parts. The inner center of our galaxies are dense, meaning they have lots of stars and solar systems. The outer part of our galaxy is less dense, meaning it contains less stars and less matter. And each part of the solar system rotates differently depending on the density of that part of the galaxy. So let's start out by looking at the less dense part of our galaxy. So if I take a star at distance r from the center of our galaxy that is rotating about the galaxy with speed v and mass m, we can describe the rotation of this galaxy using centripetal acceleration and gravitational force equations. So the gravitational force, g times the mass of the galaxy times the mass of our star divided by the distance from the center squared, is equal to the centripetal force, which is causing this star to rotate around our galaxy. The mass of our star times the speed squared divided by our distance from the center. We can see that the radius cancels out on the right-hand side and leaves us with radius by itself on the left-hand side, and also the mass of our star cancels out, giving us gm over r is equal to v squared. We solve for the speed of our star. We get that it's the square root of gm over r. So g being the gravitational constant, m being the mass of our galaxy, and r being our distance from the center of the galaxy. This means that the speed our star is rotating around the galaxy is proportional to 1 over the square root of its distance from the center of the galaxy. This means that if I graph the speed of different stars in the less dense region of our galaxy, and the distance from the center of the galaxy they are, I should get a curve that looks somewhat like this, where as you go out from the center of the galaxy in the less dense region, the speed decreases. Now let's look at the more dense region of our galaxy. So we can think of the more dense region of our galaxy as if it were a dense sphere, something like a billiard ball. If I were to take a point inside the billiard ball, it's relatively close to the center, we'll call it a distance r1, and we would take a point farther from the center of the billiard ball, we call that distance r2, these points would rotate together because they're part of the same ball. And let's see what that means for the speed of our rotation. Okay, so we know that the mass of our dense center of our galaxy is equal to the volume of our dense center of our galaxy, and because it's a sphere, 4/3 pi r cubed is our volume, times the density of that hard center of our galaxy. And so the speed of our point is equal to the square root of gm over r, meaning that a point in the dense center of our galaxy is equal to the volume of our galaxy, 4/3 pi r cubed, times the density of our dense center of our galaxy, times the gravitational constant, divided by the distance to the center of our galaxy. And so we see that our speed as a function of our distance from the center of the dense part of the galaxy is equal to the square root of g 4/3 pi, our distance from the center of the galaxy squared, times the density of the dense center of the galaxy. So our speed ends up being proportional to the distance from the center of the galaxy. So let's look at what a graph of speed versus distance from the center of the galaxy would look for this part of the galaxy. Because it's directly proportional, we see that as you go away from the center of the galaxy, speed increases. And this makes sense, because this point at r1 would have to move slower than this point at r2 if those 2 points were to move together as one. Okay, so let's recap. The less dense part of our galaxy, the speed of our stars are proportional to 1 over the square root of our distance from the center of the galaxy. In the more dense part of our galaxy, the speed of our star's rotation is proportional to the distance to the center of the galaxy. So if we were to combine these two in a graph of our rotational speed in the more dense center of our galaxy and our less dense halo around our galaxy, we should get a proportional line that rises straight up as we go from the center of our galaxy, that drops in a 1 over square root of r function as we get to the less dense part of our galaxy. This is what we expect. However, what we actually see is we get the expected relationship for our more dense part of our galaxy, but instead of the speed dropping off, it remains constant in our less dense part of our galaxy. And this is true for the galaxies we've measured, more than one, and so our expected and our measured is very different for the less dense part of our galaxy. So one way to explain this is that the less dense part of our galaxy is more dense than it appears to be. So there's more matter in the less dense part of our galaxy than we think there is. And this extra matter that we didn't see in this less dense part of the galaxy is what we've come to call dark matter. So what is dark matter? Dark matter forms halos around galaxies. And we call it dark matter, well, because we don't really know what it is. But we do know that it's not luminous, so it's not like the bright stars that give off radiation that make up the dense center of our galaxy. And it's not baryonic. It's not like the matter that we're used to. So it's not made of protons or neutrons. And so this matter that makes up this ring around these galaxies, they don't emit radiation. In addition to the stars around the outside of the galaxy rotating more quickly than they should, we have other evidence for dark matter. One piece of evidence has to do with how galaxies orbit around each other in clusters. So galaxies will orbit around each other in clusters. They orbit around the same center of mass when they orbit. And so we can judge how big a galaxy is by how much light it emits, so we know how many stars are part of that galaxy. But the galaxies orbiting each other in these clusters, they orbit as if they are more massive based on their orbital velocity than you would expect based on the light that they emit. Next, the second piece of evidence for dark matter involves the gravitational lensing effect of radiation from distant objects such as quasars. So matter, depending on how much mass it has, can bend light. And so the more massive something is, the more it can bend the light. And so we call this bending of light, we call this gravitational lensing. And so when light passes from distant quasars through clusters of galaxies, the smaller galaxies should bend the light less, and the larger galaxies should bend the light more. But what we find is that the light gets bent more by these galaxies than we would expect based on their size, which we judge by how luminous or how many stars are in that cluster. So there's more matter or more mass there than we see. The last piece of evidence involves X-ray images of elliptical galaxies. These images show the presence of halos of hot gas extending well outside the galaxy that we can see. In order for these elliptical galaxies to exert a force on these halos of hot gas at the distances we see, the mass of the galaxies must be greater than what we observe in terms of their number of stars. These measurements show that these galaxies are actually up to 90% more massive than the total mass that we can see. So the majority of these elliptical galaxies are actually made up of dark matter and dark energy. All right, that's the end. Thank you.